still sort of ended up in the rankings in the summed rankings, even with 6 fewer models. Basically, we heard a lot about different versions of AlphaFold and how you sort of change things to make it do better. So I sort of went on the same path, and I call it AlphaFold with aggressive sampling. This is actually not a gigantic pipeline of various things where you have to run this method and that method and so on. Basically, the motivation for the method was that the scoring function of AlphaFold is very good, in particular in this high region. It's really good at finding good models, so that's good. But what we have noticed is that the model diversity is not stellar. So in particular when it comes to sampling different interfaces. So here's one example, for instance, where it sampled the wrong interface, and all the 5 top models are the wrong interface. Of course, you like to have more diversity, so then you just sample more. In many cases, that just works as well, but I will see how we did it. So some way to achieve more sampling is to generate models with different random seeds, of course. That's what they do already now. They have different models, they generate different models. And already in Multimer version 2, they have also changed now, so you generate 25 model default. You can also change the number of recycles. You get not maybe model diversity out, but at least it samples more models. Or you can do what have been done in the previous talk. You perturb the input and someone sample more structures. So you sub-sample or make a different MSA. You can also change templates and turn it on. So, but what we didn't do that. We can certainly do it and improve it even more. So what we tried was to turn on dropout layers at inference to get some diversity and some perturbation to the sampling. And the dropout layers are simply just canceling out certain neurons at different layers of the network. And by doing that, we sort of allow the network to sample the uncertainty in the data. This has been used for other things when you try to uncertainty estimation for networks where you predict a score, not for generative networks, I'm not sure, but at least when you assess a score. So the dropouts in the AlphaFold network are mostly positioned in the evoformer block. So if you go into the settings, you can see there are these dropout rates. Some are 0. They should be 0 because some of these are like the outer product mean. It's not good to drop stuff there. So we just put them at these default values. There's also a dropout rate in the structure module. So we have a version of that where we don't do dropout here because we thought most of the structure prediction is happening here. We don't want it here. That was something we tried. So the overview is basically we use AlphaFold to generate models. We use the full DBS MSAs that were generated by the standard AlphaFold. So we're using exactly the same multiple sequence alignment as the NBS AF2 standard, exactly, or Multimer. We turn on dropout at inference. We have one version where we do all dropouts rates at default, and then we have one version where we have no dropout at the structure module. We use both versions of the Multiver network weights, version 1 and version 2. And we also run with and without templates. And we also run with increased number of recycles, and then we select based on the ranking score. So sort of you would plot something like this, where of course we don't have the true quality, we just have the ranking score, but then we sort of try to select a model here based on some criteria. So just to summarize here, so I realized it was not very clear. I also went back and checked what I actually did, because it was like, just looked at the actual scripts. So these were the 6 settings we tried. So we were running Multimer version, 3 versions of each for each version, and we using template or not, 2 versions. Yes, this is sort of just the vanilla AlphaFold basically, but with dropout in all cases. And then we have a couple of cases here where we do recycles, and yeah, we recycles here, and there's different numbers here. These were taken from a benchmark we did protein peptide docking, and then we realized, or we saw that the Multimer version sort of likes more recycles, more prone to, it can be more sampled basically in a way, because in general all the scores were higher for Multimer version 1 when you do more samples. And we wanted to use dropout since this is just the difference between the maximum and the minimum generated models. So we get a larger spread of model quality when using Dropout, which we wanted. So we use that for all. And then the amount of sampling we did per target is, so here are some of the targets. So we tried to generate these numbers. Sometimes when we saw the score was a bit low, we generated a bit more. This maybe I submitted the script too many times in this case. These were actually the targets that no one got right, so it didn't help. In terms of CPU hours, I checked the amount of hours I used on the cluster, and it's sort of equivalent of 8 GPUs during the CASP. So it's sort of the equivalent cost of going to this conference without the flight. So, oh, not that it's expensive. Okay, so how did we do the selection of the models? So we get this, we don't have this, but we have the ranking confidence. So our selection strategy was actually hurting us in some of the Capri estimates, I realized, because we went for diversity. So we selected first the highest ranked model as rank number 1, and then we filtered based, the next model was the one that has the highest ranking confidence, but the MM-align score should be about 0.8. So in this case, we would then choose this one down here, which was actually wrong in that case, and then we would choose different models to select in this case. Okay. So the origin of the rank 1 models in CASP came basically 50-50 from version 1 and version 2. 50% of the time we used templates, 30% of the time it came from using new templates and recycles, and 20% of the times new templates. And this I did just last night when I compared what would have been the best combination. So we decided to using this to generate all the models. Would it have been better to use any other combination of this or just running something else? So this was running all. It turns out actually running just the one with the recycles, it would actually been even better. So you don't need to do other things. You can just do this one. No templates, recycles. Would have been better in this CASP. So this is what some performance I generated before the result was out. But then I was, my goal was to be better than the baseline, because we're using basically the same input. We just run it a little bit different. And when we compare to the baseline, so here we are actually doing pretty well for some targets, improving them. We are doing worse for 2 of them. We will look at them as well. And then I created this plot. I don't know if you can see it, but basically this is one where you start from the this is MM score and the ranking for the base, and then there is an arrow for the one where I run my method. And then so what you can see is that all arrows are basically pointing in the right direction. So you're increasing the score, which is good because we're sampling. We want to get a better score. We're also getting a better quality. So this one improves down here up until perfect. So there are a couple of ones that really goes from mediocre to almost perfect. Some gets a little bit worse, but this is still where this is bad in all cases. These are also the cases where it fails or makes fails. But I mean, you get the worst model. So how much sampling is actually needed? So I just checked how much sampling. It's clear that generating 25 is actually a good thing in the standard one, but doing more is even better. But maybe 1,000 would have been enough. This is also comparing the rank 1 compared to the best. So it's still like a margin here for quality assessment to actually select on these models and maybe select a better model. So this is the room for improvement. So the ranking score improves the performance. So by doing this ranking, I can actually improve the confidence ranking, which was also my target. So I also generated more if there wasn't any confidence below 0.7, then I just generated more. Yes. So just look at some targets. So this is one of these non-models, I think. So in this case, so here's how the sampling looks. So this is baseline. So this is sort of how I will show a couple of these. So I have a baseline here. Dashed line is the first ranked. No, solid line first line ranked. Dashed line is the best ranked by the base methods, and it's also like you also actually have the individual ones there as well. So baseline submits here. Then I do sampling. You generate bad model, bad confidence. So that's good. And then good model, good confidence. that's really good. So I'm able to select it. So, but also a little in between here as well. It seems like it's going here. So a little bit. And then this is comparing then the baseline model, which is actually completely wrong. This might be sort of a problem with this score. You tend to get half, and then it's just like this half of the one domain is right. So it's not the perfect score I had at the time. So obviously, this one should probably have 0. Here's another one, same thing with this. It's able to sample quite a few with high quality, but they still have a bad score. But then there are a few here that actually then are up to be selected. So that's a quite remarkable. There's sort of something happens here that you're able to detect. You get like a high ranking confidence, able to select this one. With just this pool of models, I would just have select something down here. Or this one is actually really accurate. It's like you have really sidechain accuracy here in the interface. All sidechains are basically in the right place. Here's this one that's been shown 2 times. I think it's me and Venklovas who made good predictions for this target. And same thing here. It looks very similar. It's like it's doing a lot of sampling, and then actually I'm able to select it here. So I'm a bit lucky that I got this once. So maybe maybe you need like to do a lot of sampling to actually generate a score, which I've seen before, like in when we're doing a lot of, for instance, with Rosetta, you were running a lot of, you needed to relax a lot of structures to actually generate the scoring. Maybe you need to do a lot of scoring to actually understand that you're doing right. Or yeah. And yeah, here's another one where the baseline picks a pretty bad one, and then same thing here. A lot of sampling to pick that one up. This is the second ranked, and it's not so good. Still high score. I don't know what. So this is a bit tricky. You might select that one or that one. That was just by chance you got this one probably. This is one that actually also worked. This one I tried. I just ran it without any dropout, and it also works, just generating more structures. Here's an interesting one. This is an intertwined dimer. It looks like this, so I'm able to. This is actually the 3rd ranked in this case, bit of an outlier, but it's quite complicated. It seems like it's small, but it's really complicated because it's sort of intertwined between each in the dimer. So the 1st ranked model has this, it's sort of overall right, except for this, the pairing of the sheet here in the middle that goes in the wrong direction. And then this one is, I mean, another attempt, it's still wrong. And then this one actually gets it perfectly right. So it's basically, in all cases, it's basically, except for this part, but I think you can ignore that one. It's like, okay, so let's just look at what went wrong in these 2 cases. So where it actually did worse than the baseline. That's what So what did we do there? So basically, it's sort of like a more or less a random guess on what we would pick in this case. So baseline happens to generate a model here. It's actually a really, really good model. Then I sample and I select this one. I have models that are better than the baseline, but I'm not able to detect them. All these have high confidence. So it's a bit hard to see what you can do. Maybe sample a bit more, but still you can't really improve the confidence more. And it's also this, this is another of these antibodies. Where is mine? Same thing here. Then I actually sampled 2 populations, more or less. My 1st rank is just the other populations. My 2nd rank is actually up the line there. So it's overall, I think it's sort of like a success case in that sense that sampling improves AlphaFold predictions, and it should really be easy to implement this. You can just like download the code and run it, basically using AlphaFold as is, and then increase the number of models, recycles, and then we use this dropout trick to get more diversity. And of course, there are potential improvements to get even more diversity. So you can, of course, increase the dropout rate. You can also subsample the alignment, which basically all other groups before did. So that's possible still here, and I think that will certainly improve this even further, in particular dividing it into domains if possible, because and do that to make better, and then combine this as well. So I think this dropout is one thing you can do. You can do subsampling, or you can even do the templates. So it's a bit, you like to have like a volume button where you can tune it a little bit and make it generate a little bit more diversity. So it will sample different conformations. Yes, this was it. Basically, I have a lot of funding, but no people working for me. So I basically have to do all my work myself. So, so that's, yep.
Thank you very much. Questions, please. Yes, Jean-Ling.
Thank you. Bjorn, so you show that your aggressive sampling strategy works pretty well on the nano body complex.
Yeah.
But our methods actually failed on those ones. Could you explain why your this approach particularly work well on the nano body complexes?
You could say I was lucky, maybe. Because I mean, if you look at this, it's like, I don't know, maybe I sampled a little bit more than, because I mean, see, if I wouldn't have had these 5 points, then I'm here. So
yeah, is there a particular reason, physical reason, or interaction property of this kind of the proteins that lead to this kind of sampling? Or?
No, I mean, I just sample it and then I use this to. There's not much manual intervention in this. I just sample it, so I haven't looked in detail in the results. But so this is what I have to go at. I mean, so the fact that I actually select this one, I mean, it's not like it's obvious. If I would have sampled less, at this point would not have been there, right? So, so it's because it actually has high confidence ranking, so there must be something there. But yeah.
Well, thank you for the presentation. I have one question about your results viewed in light of the Zen group's results. So the Zen group reported that when they did the MSA with the deep MSA2 tool, they selected like this combinatorial thing. And now that you have shown that if you do this forced sampling with Dropout, you can get like really good results, and they report really good results as well, but they are in this MSA field rather than the Dropout. So do you think like combining the two approaches, just aggressively sample from
definitely. I mean, it's just one other perturbation that you can do. Dropout was like an easy way of doing that. I have not many people working for me, so I could just turn on training equals to true and then fiddle around with some output files, and then I could actually make it work. So it was much easier than to like have this huge pipeline and internal stuff. So it was the lazy man's work, but it's so easy to turn on because it just works. You get some more diversity, and then I think it's like you have a sledgehammer for the MSA maybe, and then you can maybe do a little bit with the Dropout as well, and you can also increase the dropout rate as well. I tried with that, but you have to be careful because you can make everything to go into. I mean, everything can disappear. So I mean, just doing the Dropout as a training is a bit it's safe because it was trained on that, right? It's sort of that's what it was trained for in a way. So that's fine.
Okay, just before we finish, one announcement. For the SIGs, the interaction SIG will be in here. The disorder and ensemble SIG will be in SIDR. That's SEDIR. It's all changed.
So I have consulted with both Guy and Roland, and they have decided to hold their SIGs together. So let us all join in this room, and we'll somehow make it happen, I guess, combining the two. I guess there's interest on both sides to hear the other story. Okay, sorry, John.
Okay, thanks, Christoph. Okay, so thanks all the speakers this morning. I thought that was a terrific session, and see you in a bit. Sorry. Oh, what a, yeah, don't forget the posters, folks. 2:30 officially.